The next theorem is based on linearly independent vectors forming a basis in an n-dimensional space. So this theorem basically says that a vector v in an n-dimensional space can be written as a unique linear combination of n linearly independent basis vectors. This can be written in the following expression. So we have the vector v. This is being written as a linear combination of the n basis vectors. So the basis vectors here are given by this get I, v is our given vector, n is the dimensionality of the space, and vi are the components of the vector along the basis directions. So vi is called component of vector in the given basis. So we need to show basically that this expansion is unique. So let us prove this by the method of proof by contradiction. So let us suppose that the expansion of v being written in terms of the basis vectors, let us suppose that this expansion is not unique. Okay, so if this expansion is not unique, then that means we can have or at least two possible expansions. So let the first expansion be as follows, as well as we can write v as a different kind of an expansion in terms of the same basis vectors, so different components. So here we have the components vi, here we are having different set of components vi prime. So the same vector, let us suppose that the same vector can be written as different expansions having different coefficients, different components with the same basis. So from these two, what we can do, we can subtract the two, then what we will get is the following. So the left hand side is nothing but the null vector. So this is the expression that we get. Now remember that the ket I, the ket I was basically denoting the basis vectors of this vector space, and basis vectors are linearly independent. So let us write down ket I denotes the basis vectors, and basis vectors are linearly independent. And from the definition of linear independence, we have that certain set of vectors are called linearly independent when we take their linear combination and set it equal to the null vector, and the coefficients in the linear combination turn out to be the trivial solution. That is, all the coefficients should come out to be 0. Then we have linear independence. This is by the definition of linear independence. So let us write down the definition of linear independence just to remind ourselves once again. So linear independence was given by the following condition, that if we take the following kind of linear superposition for vectors I, and if we set it equal to 0, then we get all ai equal to 0 for linear independence. Now, since our I basis vectors are linearly independent, that means all the coefficients in this particular expansion should be 0, because see, we have the basis vectors I over here and we have the null vector. So if we write it down, this is basis, this is null, and we see from here the definition of linear independence, that taking linear combinations of the basis and setting it equal to the null, we get the coefficients in that linear combination as the trivial solution. That means from this equation we will get the following. Because these are the coefficients, these need to be 0 for linear independence. This would further give us that Vi is equal to Vi prime. Now this shows that we reach a contradiction, and that we would indeed need to have a unique expansion. So from here we have shown that we cannot have two separate expansions. Vi over here is equal to Vi prime. So we indeed have a unique expansion. So this gives us a unique expansion. So this proves the theorem that a vector V given in a vector space, in an n-dimensional vector space to be precise, such a vector can be written as a unique linear combination of n linearly independent basis vectors.